What we do know is that we are in the middle of a tremendous cosmic expansion, that looking out in all directions for billions of light years, that there are galaxies rushing away from each other in a state of uniform expansion. Not just rushing away from us, but rushing away from each other in a way that looks the same, whichever galaxy you happen to be riding on. And that this expansion has been going on for billions of years. And that this particular phase of expansion began at a definite time in the past. And that time, when the universe was very hot and very dense, there were no stars or atoms. Even the nuclei of atoms had not yet formed. That this state did exist, and perhaps 10 billion years ago, maybe 12, maybe 9, we don't know the precise number. About these things we're reasonably certain, as certain as we're likely to be about anything in physics. Beyond that, there's tremendous uncertainty. It's possible that this is all there is. This cloud of galaxies may be extending out to infinity, but that the whole thing started 10 billion years ago in a moment of infinite temperature, infinite density, and that the universe has just developed since then, that was the beginning of time. There is another possibility, which is getting to be more popular among cosmologists, that in fact the universe has many of these expanding regions, that they pop off all the time, and that we're just one expanding region in a mega universe which has countless of these. One bubble, and that this is happening and will continue to happen forever, and that no matter how far in the future you go, there will be new expanding universes that get a fresh start with suns and planets and perhaps life. It's hard enough to think about a universe that's billions of light years across, but to think of this, that is just a tiny little part of a really big universe, that really stretches the imagination, but it may be true. And the problem is we don't have any way of telling astronomically
Hier werkt hij, in Austin, Texas. De theoretisch natuurkundige Steven Weinberg. Gefascineerd door de vraag of het op korte termijn mogelijk zal worden om het natuurkundige en wiskundige principe waarop heel het universum berust in één formule samen te vatten. Het moment van de ultieme schoonheid. Gefascineerd ook door de vraag wat er was, ja, of er eigenlijk wel iets was aan het begin van ons heelal en de tijd. En wat er aan het eind zal zijn, als er al een eind is.
The odds are that the expansion of the universe that we see in the galaxies around us will go on forever. There doesn't seem to be enough matter around to provide a gravitational field which could stop the expansion and bring the matter all back together. Of course, if it did stop the expansion, then everything would fall back together again, and that would also extinguish all hopes for the future. In fact, somewhat more conclusively than an endless expansion would. What will happen in an endless expansion? I don't know. Freeman Dyson has written very cleverly about how we may be able to go on with an infinite number of thoughts to think by simply slowing down the rate at which we think, so that life will never end, although it will become slower and slower. The bristlecone pine is a tree that lives 20,000 years by shutting its metabolism down to the point where it's barely alive. It lives in the mountains of western United States, and Dyson may be right. It may be possible for us to do something like that. But for me, these, and for Dyson also in a sense, these questions are academic, since we will not be there to participate in this.
Weinberg heeft van huis de oude cassetterecorder meegenomen die normaal bij hem in de badkamer staat. Dit is de man die zou schrijven: hoe meer we ontdekken over de fundamentele natuurkundige principes, des te minder lijken ze met ons van doen te hebben. Dit is de man die schreef: hoe meer we ontdekken, des te onwaarschijnlijker wordt het dat deze wereld is geschapen door een bezorgde schepper die het goed met ons voor heeft. De hele avond ligt open. Een avond met een man wiens pogingen om het universum te begrijpen van een onwezenlijke schoonheid zijn. Lees zijn boeken. Lees Dromen van een finale theorie. Lees de eerste 3 seconden. En je begrijpt waarom. Hij heeft een soort college voorbereid over schoonheid en troost. Hij legt de aantekeningen op zijn bureau. Of wil je eerst praten? Nee, vertel eerst maar. Dan zien we later verder. We schrijven een donderdagavond in Austin, Texas. Planeet Aarde.
As science has progressed, as we move toward an understanding of everything in nature, there has been a certain disenchantment of the world. It used to be that when we saw lightning in the sky, we saw the hand of Jove or Thor. Now, ever since Benjamin Franklin's famous experiment with the kite, we know it's a discharge of electricity from one cloud to another, or from a cloud to the ground. Generally speaking, we understand the things that we see in nature, the things we see around us, and why the sky is blue, why the grass is green, in a very naturalistic way, without invoking anything supernatural. And nowhere has there been a greater sense of disenchantment than, I think, our view of living things, ourselves. Since the work of Darwin and Wallace in the 19th century, we know how the wonderful adaptation of living things, the fact that we can see and hear and walk and breathe and eat, how all these things could have developed without any plan, without any guiding hand, without any benevolent overseer, but through a very long series of breedings and eatings, out of which some traits that were favorable to survival developed and became what we see today. This is a little discouraging, that human beings are not the stars of a cosmic drama that has been planned from the beginning, but are part of a world governed by impersonal forces, a world in which accident plays a large role, a world in which we ourselves, our intelligence, everything we hold dear, does not appear at a fundamental level. That at a fundamental level there are mathematical equations, a rather cold, perhaps dispiriting view. So what sort of consolation can we find? Because I think we can't go back. Living in a world in which there is no longer a nymph in every brook and a dryad in every tree, what can we find to console ourselves? Well, of course, the answer is different for different people, and I'm glad not everyone chooses to be a scientist because there's competition enough. But one of the things that consoles us, it seems to me, is scientific research itself, the same sort of research that's produced the disenchantment in the first place. Because the results of this scientific research are really quite beautiful. They have a remarkable beauty that, to some extent, perhaps not altogether, consoles us for the loss of the beauty that was present in the world when we saw gods and giants and fairies all around us. In a sense, we're faced with the same sort of disenchantment that faced our ancestors in the time of great geographical exploration, when what was being learned was not the laws of nature, but just what the world was like, what there was in the world. Here, for example, is a map of the what is now the northeastern part of the United States. If you come from Massachusetts, you'll probably recognize Cape Cod here.
Yeah.
But the person who drew the map really didn't know very much. At the time this was prepared, in the early 18th century, very little was known aside from the coastal region of North America.
Of the interior.
And in the interior, you can see that they've put animals. Some of them are recognizable, like I think that's a antelope of some kind, but others are hard for me to understand. It must have been wonderful to be a child, even as recently as the 18th century, and look at a map of the world and see large empty regions like the northern part of Canada, which would be beyond the edge of the map, and to imagine all the strange animals and people that live there, perhaps people with strange customs. You know, Othello, when he talks to, when he explains how he won the hand of Desdemona, explains that he did it partly by describing the travels he's taken to the strange parts of the world where there are anthropophagi, cannibals who eat each other. Well, that sense of mystery about the world, how there are great unexplored spaces, is pretty well gone. Today we have a vision of the world which doesn't leave much to the imagination. This is an aerial photograph of Chicago. I think I've got it the wrong way. It doesn't make a great deal of difference. You can see clearly all the city streets, and there are no mythical animals here. And actually, this sort of picture can be shown with much greater magnification. I understand it's possible to get satellite photos which allow you to see individual automobiles, or
license plates, and,
perhaps license plates. And maps like this aerial photograph, now exist for every part of the world. There is no part of the surface of the Earth which has not been photographed in this fashion. And there really is no more room for mystery in this. And that is saddening. I found a nice quote recently, quoted by E.M. Forster in an essay by a Lombard physician, Girolamo Cardan, writing in 1571. And he was saying just about what I've been saying. This is Cardan speaking now in 1571. It has been my peculiar fortune to live in the century that discovered the whole world, America, Brazil, countries to the north and east and south. And what is more marvelous than gunpowder, the human thunderbolt, which in its power far exceeds the heavenly? Nor will I be silent about you, magnificent magnetic compass, who guides us through vast oceans and night and storms into countries we have never known. Then there is our printing press, conceived by man's genius, fashioned by his hands, yet a miracle equal to that of the divine. And but then, after this excitement and exhilaration of all these discoveries, Cardan then goes on and sees the negative side, the sad side. Heresy has grown. The arts of life will be despised. Certainties will be relinquished for uncertainty. He then was reacting to the developments of geographical exploration and technology in the way I'm describing that the human race has reacted to the discoveries of science. This process, of course, continues now. The work that I and my colleagues do in physics is aimed at perhaps reaching a final point of understanding, not of solving all the problems of science, that will never happen, not of understanding everything, but of understanding in some fundamental way why things are the way they are, of reaching a final theory which has in it potentially the explanation of everything we see, even though the world is too complicated actually to explain on the basis of solving physics equations. And in this process, one of the things that consoles us is the increasing beauty of our theories as we develop them. To the beauty of the equations of physics is hard to describe. I've thought about how to characterize it, and I suppose the best I can do is that it's the beauty of inevitability, that looking at a scientific theory, if it's a compellingly beautiful scientific theory, one has the feeling that nothing could be different, that everything is in place because it has to be that way. And this is like the beauty of some works of art. For example, here is a two-part invention of Bach, just the beginning of it. Simple, austere, every note in place. You couldn't change anything. If you listen to it and it was played badly, I don't have any recordings of music played badly, unfortunately, but if it went da 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 da, you would know it. Even if, like me, you don't know anything about music theory and can't play an instrument. Hearing da 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 da, you would know that there was a wrong note there. You might not be able to explain it. In fact, I would not be able to explain how I know that's a wrong note. But it would clearly be wrong. I suppose you could say that being exposed to the great music of the Western heritage from Bach on and before, we have, without particularly seeking it, earned a certain education in music. We know what to expect. We know how music hangs together. I don't know to what extent this is a purely cultural phenomenon, whether this would carry over to an entirely isolated society, but at any rate, within the Western tradition of music, we can sense a wrong note without knowing why it's wrong.
Yeah.
And in the same sense, our sense of beauty in physics has developed to the point where we can judge sometimes even the validity of a scientific theory by the extent to which it satisfies that sense of beauty. And more than that, in a sense, it is the beauty of a theory that we are seeking. At any one moment in the history of science, there is always a tremendous wealth of data, factual information earned by experimentalists. Most of it correct, some of it wrong. Always is a mixture of some right and some wrong. But even if you assume it's all correct, there is no one unique way of representing this data with a theory. In a sense, a table of data itself is a theory. It agrees with the data. But you can find less trivial examples of many ways of fitting a limited, finite amount of experimental information with a variety of theories. The theories we are searching for are the theories that explain the information in a beautiful way. And that beauty is itself a kind of consolation for what the scientific theories have taken away from us. To explain what I mean, here are some equations, and please don't worry, I'm not going to try to explain everything on the blackboard. This is the theory of Newton, written in a modern notation, that describes how particles move. I made a mistake here. I should use the letter X consistently. How particles move under the influence of their mutual gravitational attraction. That is Newton's theory of motion and gravitation applied to a set of point particles like the planets in the solar system, treated as points, interacting under their gravitational attraction. This is the general theory of relativity of Albert Einstein, covering essentially the same sort of phenomena. Particles moving under the influence of their mutual gravitation. Now, I think almost all physicists would agree that this is a more beautiful theory than this, that Einstein's theory is more beautiful. Well, it certainly isn't more beautiful in the sense of involving fewer equations or being simpler to explain. There's a lot there. In what way is this Einstein theory more beautiful than the Newton theory? Well, all of these equations come out of one grand idea. The idea that gravitation is nothing but an effect of the curvature of space and time, and that particles under the influence of gravitation will move in straight lines, the equivalent of great circle routes on the surface of the Earth, which are the shortest distance between 2 points, between, say, Amsterdam and Austin. There is one great circle route. The particles move on great circle routes through curved space-time. That's what this equation says. And this equation tells us how, these two equations tell us how the geometry is determined by the matter, and this equation tells us how to put together the particles' positions into a symbol which expresses the amount of energy and momentum of the matter. It's much more complicated mathematically. It's much simpler physically because it all comes from one idea. And the best sign of it is its rigidity. This theory of Newton's was invented to explain the observed motions of the planets in the solar system. This, too, for example, is the famous inverse square law of gravitational attraction. The fact that the force drops off like the inverse square of the distance is expressed by that number being a 2. If that number was a 3, we would call it the inverse cube law. Why is it a 2? That's what fits the data. It could easily have been anything else. In fact, as far as Newton is concerned, it could have been 2.01. It would have also fit the data. There is an arbitrariness in Newton's theory, which is not present in Einstein's theory. There really is nothing here that you could change. Any attempt to fiddle with these equations will lead to nonsense. Certainly would violate Einstein's underlying understanding of the geometric nature of gravitation. And furthermore, this theory, Einstein's theory, explains Newton's theory, including the factor of 2 there, the inverse square law, as an approximation which is valid when the particles are moving slowly. So with Einstein's theory, we have a much simpler view of nature based on a grand idea about curved space-time, which explains why Newton's theory is the way it is without allowing any uncertainty about it being inverse square law. There's no way from Einstein's theory that you could get anything but the inverse square law. That's the kind of beauty that we find in the laws of physics. And as I indicated with my example of, I just love listening to it. As I indicated with the example of Bach's two-part invention, it is a beauty that we have been educated into through experience with nature. The beauty we find is not just an expression of personal pleasure about which different physicists may disagree. In fact, we often do disagree. But there is a sense of being right or wrong, because the right sense of beauty is the one that leads you to the correct equations. At the very root of things, at the most fundamental level, there is a beautiful description to be found, a very simple idea which underlies all the laws of nature.
How can you be so sure?
I'm not sure. I'm not sure. But it may be true, and it may be that the beauty we find in a theory like Einstein's theory is a reflection of that. 'Twas but a dream of thee, is a dream of the beauty at a much deeper level of the really fundamental theory. Now, of course, when Donne was talking about 'twas but a dream of thee, he was talking about a mistress, or perhaps it had some religious significance, and with Donne the two are difficult to disentangle. But I'm talking, the dream is the dream of the final theory, a theory which is itself beautiful and whose beauty we see reflected imperfectly in the theories we now have.
You wrote, the usefulness of our sense of beauty is a sign of our progress towards a final theory.
Yes, I think it may be. Now, you ask, though, a very good question. How do we know that there is a beautiful, simple description of nature underlying everything? And we don't know, but there is a reason for suspecting it. And the reason is just the increasing simplicity of the ideas which describe nature. The description of nature that we have now is infinitely simpler than it was in the 19th century, when there were separate sciences like physics and chemistry and biology, which were not thought to have any real relation between. I mean, there were laws of chemistry and there were laws of physics. Laws of physics were divided into laws of optics and mechanics and electricity and magnetism. There had been a mild unification in the work of Maxwell that unified optics and electricity and magnetism. But now, so many of these things are brought into a common framework. Nature has gotten, if more esoteric, more mathematical, more impersonal, still much simpler in the way we look at it and describe it. Now, I can imagine this growth in simplicity going on for many years to come, but I can't imagine it going on forever. How can things get more and more simple? They could get more and more complicated, but more and more simple, you would think eventually it has to come to an end. It has to converge to something which is the final simple theory. But I don't know that that's true. The concepts are increasingly foreign and impossible to explain except in mathematical terms. The most adventurous theoretical physicists today have almost succeeded in giving up the idea of space and time, except as phenomena that arise at a certain level of approximation, but which do not appear in the underlying equations. For an ordinary physicist who lives in the world of particles colliding and electric currents and rays of light, it's very difficult to imagine formulating the equations that govern nature without having space and time in at the very beginning. And yet that's the way the leading theorists of today are going. This is hard for me to understand. And the mathematics that goes into it is mathematics that physicists of my generation certainly didn't learn. Although we are comfortable with the equations of Einstein and Newton, we did learn that mathematics when we were in school. I've been pretty cautious about imagining what the final theory is. I think there was a time.
You're sure about its beauty. But
well, I'm sure about its beauty because if it isn't beautiful, we won't recognize it as the final theory. We will say, well, why is this what it is? And we will look for something more beautiful. So it may be the final in the sense that it's the best we can come up with, but it won't be what our heart's desire is. You know, it's just like you could say, I'm sure, I don't know who I will marry, but I'm sure that she will be beautiful because I won't marry her otherwise. And in my case, it did work out that way. I would say that principles of symmetry are one form of simplicity and inevitability. A symmetry principle is a statement that something looks the same from different points of view. Yeah. If you look at my face, you see little difference between the left and right. It's not perfect symmetry, but the human face is pretty good bilateral symmetry. The other things have a much higher degree of symmetry. A cube, I don't have one handy to show you, but a cube.
No, this is not a cube.
Well, we don't have any cubes here, but a cube would look the same.
We can imagine.
From a number of different directions. You can look at the cube from top, from the side, it looks the same. A sphere has even more symmetry. These are just the symmetries of things, and they are of only minor significance. I mean, certainly it's not the most interesting thing about a human face is that it's symmetrical between left and right. The symmetries that are interesting to the physicist are the symmetries of laws, the symmetries that say the laws of nature don't change when you change your point of view. Mm-hmm. For example, if I move my laboratory from Texas to Amsterdam, which I'm not proposing to do, I will discover the same laws of nature. The world will look different. The days will be shorter in winter. There'll be more rain. But so I will notice that there's a difference. But the laws, the physical laws, will be the same, whether discovered in Amsterdam or in Austin. And the symmetries of nature are the variety of different changes of point of view, which have that property that they don't change the laws of nature. And they involve translation, as I said, the movement of the laboratory from one position to another, rotation, the change in the orientation of the laboratory, and several others, some of them having nothing to do with space and time, some of them having to do with how we identify the elementary particles. There are symmetries that say the laws of nature don't change if everywhere I see this particle, I replace it with another particle, and vice versa. Or more complicated transformations can be done. Very often, when we don't understand the forces, that we can still detect the fact that there is a certain degree of symmetry present. And in fact, when I was first a graduate student, much of the work of elementary particle physics had to do with working out the symmetries, because we had no idea of the nature of the forces that were acting on the particles. And all we could do with any degree of confidence was to discover and test the symmetries of the particles. Now we're in much better position. In fact, now we're in a position where we recognize that the nature of the force itself follows from the symmetries. The forces are dictated by the symmetries. They could not be other than what they are. My favorite example of this is gravitation as viewed from Einstein's point of view. It requires me to do a little demonstration standing up, but if you don't mind, I will. If I stand here, my arms hang loose at my side. Now if I twirl around, I'm not going to do it very fast, but if I did this very fast, my arms, are drawn up. And then if, like an ice skater, I bring them down, I spin even faster. My arms are drawn up when I spin by what we sometimes casually call centrifugal force. And from the point of view of Newtonian mechanics, the reason that this effect exists is because you should really write the laws in a frame of reference which is not rotating. And it's only in that frame of reference that Newton's laws in their simplest form hold. And what you see when you rotate is the effect of the change of the frame of reference. Now, from Einstein's point of view, the answer is quite different. Einstein's point of view about space and time says that all frames of reference are equally good. The laws, it's a principle of symmetry. There are different ways of measuring, including working in a rotating laboratory, so that you measure positions and times differently than if you were not rotating, and they're all equally good. So how does Einstein explain the fact that my arms are drawn up? Why does that happen when I spin and not when I just stand still? Well, Einstein points out, actually following Ernst Mach in this, that when you spin, there's something else that changes. If you look at the stars, you'll see, from a spinning point of view, they're rotating around the zenith. If you sat in a laboratory at night and you looked up at the sky and the laboratory was rotating, you would see the sky rotating around you. Mach asked, without being able to answer the question, is there some effect of the rotating universe which creates the effect of centrifugal force? And Einstein answered the question and said, yes, indeed, it is the force of gravitation. Now, ordinary gravity, as described by Newton, can't do that, because ordinary gravity, the kind of gravity we're familiar with in everyday life, is just simply an attraction, and it can't do that. But in Einstein's general theory of relativity, a rotating body not only attracts things, but also sets up a field of force which is a little like a magnetic field. And the rotation of the whole heavens around us produces, through Einstein's form of gravitational equations, the centrifugal force that pulls our arms up. So in other words, now, if gravity didn't exist, there could be no symmetry between the rotating frame of reference and the frame of reference at rest. So therefore, the statement that there must be a symmetry, the demand for symmetry between these two frames of reference, requires the existence of gravity. The existence of gravitation can be deduced from that symmetry principle, because what else could be producing the centrifugal force? Some force. And that force, when you work out its details, is just the gravitational force as described by Einstein's equations. And today, the other forces of nature, electric, magnetic, weak nuclear forces, which are responsible for beta decay, for radioactive decay, and for processes in the sun that produce the heat of the sun, and the strong nuclear force which holds the quarks together inside the nucleus of the atom. All of these forces, all the forces we know in nature, arise from principles of symmetry and can be explained in terms of principles of symmetry. So principles of symmetry are the deepest things we know about nature. And it may be that a truly fundamental theory will be simply encapsulated in one simple statement of a symmetry principle. We don't know what that is. It may have nothing to do with ordinary space or time, may have nothing to do with the particles we see in our laboratories today. It may be very hard for us to guess. Maybe we're not smart enough to figure out what it is. But I would not be at all surprised if, at their deepest level, the laws of nature took the form of symmetry principles. This beauty of the laws of nature is satisfying to the physicist, but it's a rather austere and limited form of beauty as compared with what you find in the arts, which touch us much more deeply, which say much more to us about ourselves and about the problems we face in living our lives. And I would say that the beauty of physics would be a very bad model for the arts to try to imitate, a very bad exemplar in several ways. The ideal of rigidity, of every note being in place, well, that's true of a two-part invention by Bach. It's true of certain paintings. But you know, there are grand works of art, like the plays of Shakespeare, for which this is not true at all. Think, for example, of the Gravedigger Scene in Hamlet. Hamlet is a rather brooding, austere play. There has been a tragedy. The previous king is dead. Hamlet is trying to decide what to do about this. He senses treachery. He can't quite make up his mind what to do. His sweetheart kills herself. Things are moving toward a climax when Hamlet will confront his uncle in the horrible last scene where everyone dies at the end except for Horatio. But just before that climactic scene, there is an episode that seems totally out of place, the Gravedigger Scene. And yet the Gravedigger Scene, for reasons I've had a difficult time explaining to myself, has always seemed to me the high point of the play. This has nothing to do with the plot. Hamlet is looking for the grave of Ophelia in the graveyard, and he comes upon an open grave, and there's a gravedigger digging, and he has this comic conversation with the gravedigger with a lot of silly puns. And this gravedigger scene of Hamlet violates what we've learned from Aristotle about the way to write great tragedy. Aristotle taught that we have to have unity of point of view, that there couldn't be discordant elements, that the tragedies had to be about great figures, princes and so on. And the Aristotelian ideal was picked up by Racine and Corneille and the great classic French tragedies. Here, Shakespeare is violating every principle of Aristotelian drama criticism. He has this comic proletarian. It has nothing to do with the story. You could have left out the scene. You know, the play would make perfect sense without the gravedigger scene. Why have it in there? Well, for a number of reasons, I think. It provides a kind of comic relief. It lets us rest for a moment before the final horrible tragedy in the last scene. But also it reminds us that while these princes are having their high-minded tragedies, there's a world out there of ordinary people digging ditches. It also reminds us a little bit about the reality of death. Hamlet is worried about sending Claudius to heaven if he kills him. The ghost has come back from the grave. Hamlet has quarreled with a priest over the burial of Ophelia. And here this comic gravedigger says, you know, this dust that was Alexander the Great may now be used to stop a hole in a wine barrel. Um, it's a reminder of the earthiness of the reality of life and death. Uh, that, I think, to me, that is art at its highest. At its very greatest level, it reminds us of the nature of humankind, which is never simple. Human beings are not what they are because they couldn't be anything else. A character in real life can never be really predicted.
Mm-hmm.
And so I think that the beauty of the arts, which is like this, that's certainly a beautiful piece of music. I can't stop playing it. But that's not art at its highest. That's not the art that really tears our hearts out. As a result of, I think, of the disenchantment of the world by science, there have been a variety of reactions to science, which I think are quite misguided. One class of responses to the challenge that science presents to an older, more traditional way of looking at the world is to try to pick over aspects of science that will somehow restore a sense of enchantment, a sense of man-centeredness, or I should say human-centeredness, to the world. This has come up recently in discussions of quantum mechanics and free will. Quantum mechanics is the way that was developed in the 1920s of looking at the world at a very fundamental level. Quantum mechanics governs everything, but you don't see the effects of quantum mechanics as different from, say, Newton's mechanics, unless you look at things that are very small, like atoms. And no sense could be made out of atoms until the discovery of quantum mechanics. One of the things about quantum mechanics, which was so strange when it was developed, that it seemed to deal only with probabilities. If you ask a question about what will happen if I fire one atom at another atom with a certain energy, will it be scattered? In what direction will it be scattered? Will the atom be excited? All of these things can be answered by quantum mechanics, but the answers come in the form of statements of probabilities. There is a probability of scattering, there's a probability the atom will be excited, there's a probability radiation will be emitted. The physicist using quantum mechanics seems unable to answer any question except in such language of probabilities. Now, there were many who were repelled by the old determinism of Newton's theory, the idea that given any system, knowing where everything is at the beginning, knowing how fast it's moving at the beginning, you could then tell with absolute certainty where everything would be in the future. This seemed to take away from human beings their freedom. It opened up the possibility in some future age that a scientist may be able to predict precisely what you were going to do. And as such, it challenged the sense of free will that we all have. We all live our lives feeling that we can decide whether to go to the blackboard or not, sit down, play the music, whatever. And so when quantum mechanics came along, and this continues to the present day. I recently read a book by a professor of divinity who picked on quantum mechanics as a saving grace of physics. When quantum mechanics came along, it seemed like a release of free will. At last, nature was no longer deterministic. At last, it was possible to have some uncertainty, which allowed room for us, for you and me, to make up our minds about what we were going to do. I think this is a typical example of seizing on a particular aspect of science to try to restore a pre-scientific way of looking at things. And I think it's quite mistaken. I think it's quite mistaken for a number of reasons. One reason is that it really doesn't restore very much of a sense of free will merely to have uncertainty. I mean, after all, suppose you believed your mind was a machine in which everything that happens is absolutely dictated by the previous condition, and there was no freedom at all, and you had no free will, but there was a little part of your mind was a roulette wheel. And that roulette wheel every once in a while would spin and come up with red or black, and that would determine what you do next. You might, if it's red, you would do one thing. If it's black, would you then feel you had any more free will than you had without the roulette wheel? Does having a roulette wheel in your mind give you a sense of free will that you wouldn't have without it? Mm-hmm. So that's one reason I think this is quite wrong. Another is that it really overstates the extent to which quantum mechanics does remove the determinism of Newton's physics. I have to admit that was the point of view of Niels Bohr and some of the great founders of quantum mechanics. But quantum mechanics itself is described in terms not of the motions of particles, which have to be described probabilistically, but in quantum mechanics there is something that evolves with time called the wave function. The wave function has contained in it all the information about the probabilities of different experiments. And as long as the system just develops by itself, the wave function changes with time in a completely deterministic way. If you know what the state of the system is at one moment, then you know what it is at any future moment. In fact, the complication due to chaotic behavior, chaos, which occurs when you have complications in classical mechanics, doesn't occur in quantum mechanics. Quantum mechanical systems are never chaotic because the equations are so simple. They're of a kind called linear. And now for Niels Bohr, something happened when you made a measurement that couldn't be described by the wave function. And most of us now feel that that's not a very satisfying picture of quantum mechanics, and that what we really have to do is think of the particles that we're studying and the apparatus we use to study them and the mind of the physicist and the journal in which he or she submits his scientific article, all as described by one big wave function, which means that there really isn't anything probabilistic at the core, although it's convenient to describe things in probabilistic terms. This is a subject of great argument, and this is not a settled issue. But it's not clear that quantum mechanics, in fact, represents a departure from the strict determinism of Newton's theory. And there are many people who shape quantum mechanics today in a way that does not introduce any probabilities. But I think perhaps a more fundamental point is that none of this, it seems to me, has anything to do with free will. I play the music. Now, why did I play that? I did it because I wanted to.
Why don't you go on?
Well, there's no doubt. I also wanted to turn it off because I wanted to talk.
Okay.
There's absolutely no question about why I turned on the music. It was because I wanted to. There's no question. I had free will. Then you can ask, why did I want to? Now, I'm not sure why I wanted to. I think I wanted to because I like hearing the music and so on. But if I then ask why that, why do I like that kind of music, I get into questions that I can't answer. And it may very well be that, at least in principle, we could make a completely deterministic picture of human behavior in which my turning on the music was predetermined, could have been predicted by anyone who had studied me carefully enough. But part of that prediction would be my act of free will. Part of that prediction would be my personal choice to turn it on. And I don't feel the fact that that could be predicted removes the experience of choosing to do something. So I think that this example stands for a whole host of other examples in which those who are appalled by the coldness and the impersonality of science, I think, are looking for the wrong things in science. Well, I don't think it'll say anything much about life or consciousness. I think that it will confirm, when we have it, that the universe is governed by impersonal laws that are not that do not directly relate to consciousness or human goals. But we already strongly suspect
the more and more you discover, the more and more we humans disappear out of the laws of physics.
That's right. Now, that's a process, as I said, that's the disenchantment of the world. Right. That's been going on for a long time, and this will confirm it. This will be the final disenchantment. But it will still be true that human life, all life, consciousness, are governed by these laws and did arise, improbably as it may seem, here on Earth through a series of events which are capable of being understood within this general framework. I don't think that the discovery of a final theory will help in the slightest with understanding the nature of intelligence or consciousness.
Or what we are doing this afternoon.
Yes, that's right. I don't think it will help that at all, except that it will put a final period to the long sentence that science has been telling us about the nature of the world, that it is governed by impersonal laws. Yes, I think a certain sadness. I would like to believe that when I died, I would go on to some other life, that I would meet my wife again in a future life. Tennyson's Ulysses, when he talks about setting sail beyond the sunset in the baths of all the western stars, what he looks forward to discovering is the Happy Isles, and we'll see the great Achilles, and all the heroes whom we knew. Well, I'd be content to just see some of the people I've loved here on Earth. And there's a certain sadness in having to give that up.
Did you ever believe in a God? A Messiah?
I never believed in any particular religion. I think I did believe in God when I was pretty young, but and I don't recall how I became disillusioned with that. But at a certain point, it just seemed to me so silly, and it's hard to use the word silly about a belief that's governed so much of human history. Yeah. And has caused some good and some very great art, as well as some terrible evil. So I wouldn't just use the word silly, but I guess that's the way I felt about it when I was young. But you know, the fact that one gets some sense of sadness in giving up the belief in the supernatural is at the same time a warning to us that belief in the supernatural may be just wishful thinking, because we are giving something up when we do give it up. How much of human history has been governed by concern about life after death? You know, I referred earlier to Hamlet. The whole play is filled with worry about life after death. The great speech, to be or not to be, and he decides not to kill himself because of the untraveled world from whose bourne no traveler ever returns. Makes us rather bear those evils that we have than fly to others we know not of. My God, in Egypt, they devoted the whole gross national product to building these huge tombs just to protect the body of the ruler. This, I think, must have been a preoccupation of human beings from long before there was any writing, any history. Our ancestors 30,000 years ago must have worried what happens to them after they die. It's hard not to, and to realize that there is nothing there. It is chilling. It does require some consolation, and part of the consolation is just to be able to face the fact without flying to some kind of supernatural comforting. You know, they're really two quite separate questions, although people always put them together. One is there a God? Is there a creator who has organized things, who has set out a divine plan? And the other is that God a good God?
A moral God.
A moral God. Now, it's quite possible to believe in one without the other. I mean, after all, the fact that you are the creator does not necessarily mean that we have to approve of your creations. You may be a prisoner in a prison camp and have to live your life in complete compliance with what the commandant of the prison camp orders. And the commandant may govern your life and may be able to punish you in horrible ways if you disapprove. But you still have deep inside you the capability of judging. With Job speaking to God, who has tortured him to win a bet with Satan, asks God, how could you do this when I have done no wrong? And God answers, in effect, shut up, I'm bigger than you are. It's not an entirely satisfactory answer. Looking back at the writings of our own religious tradition, the Jewish and Christian religious tradition of Europe and America, it doesn't seem to me entirely admirable morally. And certainly it has led to the most awful consequences. Here in the United States, before our Civil War, slavery was practiced in the South. And even people who were very good-hearted people defended the institution of slavery with great sincerity, I believe, because it was dictated by religious teaching. The slaves are the children of Ham, and God has ordained that this is their position in life. I don't see that religion has been a plus morally. Uh, Many religious leaders are very fine people, but I think they're fine people not because they're religious leaders. And I think just as the human race has woken up from the dream of nymphs and dryads and Thor and Jove hurling lightning, sooner or later we'll wake up from this fairy tale. Yes, that's my definition of the way that science provides a consolation to the tragic view of human life. This view of human life, what I refer to as the tragic view, is certainly not unique to scientists. It's some people call it the existentialist philosophy that sees human life as having no preordained purpose, not being part of a cosmic scheme of that human beings are subject to the slings and arrows of outrageous fortune, as Hamlet says. This tragic view is common to many people, and one of the consolations is to face it and to still try to understand nature. And in this way, we're not simply blind, as Yeats said in a poem, a blind man battering blind men. We're not just that. We have a little vision. We see a little bit what we're doing. And so it gives a certain grace to our tragedy. We're not entirely farcical.
Thin consolation.
But it's a thin consolation, yeah. I remember when I was a boy, I used to spend some summers in the Adirondack Mountains of New York State, where the sky was very dark and clear, and you could see the Milky Way very clearly. And I haven't seen it that well until fairly recently. I went to visit a friend on a ranch in West Texas, and after dinner we sat outside and looked at the sky, and there it was. Now I knew considerably more about it, but still the thought that this band of light across the sky is made up of countless stars, and these stars are just like the ones that we see, Sirius and Betelgeuse, and, well, it was the summer actually. The stars we were seeing were Vega and Altair. They're just like those, but so far away that they blend together into a continuous wash of light. So this galaxy we're in is so much bigger than just the neighborhood of our own stars that we're familiar with. And this is just one galaxy among hundreds of billions of galaxies that we see in all directions. It is amazing that we can understand anything, but you know, when you look at the light from those distant galaxies and you send that light into a spectroscope and break it up into its colors, you see there in the orange part of the spectrum a double line, and it's the same double line that you see if you look with a pocket spectroscope into a fire in a fireplace. It's the line of sodium, and it's the same orange color that you see if you're in a city that's illuminated by sodium lights, and it's the same frequencies shifted to the red because of the motion. But aside from the general shift toward lower frequencies, the same spectrum is emitted by sodium at the furthest reaches that we can see with our telescopes, as when we look into the fireplace in our own home. The uniformity of physical law and the fact that human beings are able to calculate what that spectrum is. We know why sodium emits light at those frequencies and not some other frequencies, and absorbs it at certain frequencies and not some other. We understand that. And it applies to the way the universe was 10 billion years ago, when that light was emitted that's been traveling to us for all those billions of years. Well, it's really very impressive. Maybe it isn't such a thin consolation after all. It takes a certain amount of, should I say, courage? Well, at least a resignation to accept a world in which we are not so important. But such as it is some consolation that at least we can look at the world as we find it, not as we would wish it to be.